Welcome back. In this video, we're going to talk about the principle that we call like dissolves like. This allows us to predict whether a solute will be soluble or insoluble in a given solvent based on the intermolecular forces of those substances. So let's talk about how intermolecular forces affect solubility. Again, we use the term like dissolves like. What this means is that if you have polar solvents or ionic compounds, and they dissolve well in other polar solvents. Excuse me, if you have a polar solvent, this will dissolve polar and ionic solutes. However, nonpolar solvents will tend to dissolve nonpolar solutes. If you mix a polar and a nonpolar solvent and solute, then they won't mix very well. So dissolution is going to be most probable when the intermolecular forces that are broken are similar to the intermolecular forces that would be formed. So for example, in the test tube labeled A, we have water, and in test tube labeled B, we have water. In test tubes labeled C and D, we have heptane. Heptane is nonpolar, water is very polar. If you take and try and dissolve an ionic compound like copper sulfate into the water, it will dissolve. Notice, however, in test tube labeled C, it does not dissolve in the heptane. It remains as undissolved solid particles. Within the water, we try and dissolve nonpolar iodine, and you can see that it does not mix well. However, in test tube labeled D, the iodine mixes well in the heptane and spreads throughout the entire test tube. So what we see here is that when molecules have similar intermolecular forces, they will mix well. What about if we have a hydrocarbon chain? So we know already that the length of the hydrocarbon chain is going to affect the polarity of a molecule. Therefore, it also will affect its solubility. So we've used this term already. A substance is miscible when it is soluble in all proportions. So for example, if we take cyclohexane and hexane and try and mix them together, it doesn't matter if you have a 50-50 mixture or a 20-80 or a 90-10, they will mix well with each other. Similarly, ethanol and water are miscible. It doesn't matter how much ethanol you put in water, it will mix and form a solution. However, again, if we put two substances together that are not soluble, we say that they are immiscible. So for example, cyclohexane in water or hexane in water, they will not mix well. And we end up seeing then a separation between those two substances. Table 14-4-1 in the ebook elaborates on this idea. What we can see is that for a given alcohol, when you increase the number of carbons in its chain, it becomes less and less soluble in water. However, it becomes increasingly soluble in another nonpolar substance, in this case, cyclohexane. So when we look at molecules, not only do we need to evaluate the types of intermolecular forces, but also essentially what proportion of the total those intermolecular forces play for that molecule. Let's take an example here. We're going to look here at 4 different vitamins and evaluate which ones will be soluble in water versus fat. So vitamin E, would you think that this would be more soluble in water or fat? Hopefully, you would identify that this is, while it does have some polar regions, it's mostly nonpolar. Fats are long hydrocarbon chains. And therefore, vitamin E would mix well with fats. What about vitamin B6? You should recognize that vitamin B6 has a much higher proportion of its total surface area is being polar, it can interact with water via hydrogen bonding in a lot of different locations. Therefore, this will be more soluble in water than in fats. Vitamin A. Vitamin A, we see, has one region that's polar, but the vast majority of the molecule is non-polar. So we would expect it to not dissolve well in water. Finally, vitamin C. Vitamin C has lots of polar groups and lots of areas that can interact through hydrogen bonding. Therefore, it will dissolve well in water and not very well in fats. Here's one final problem. Put the following compounds in order of increasing solubility in water at 25 degrees Celsius. Pause the video and try this on your own. Welcome back. So in order to determine solubility, we need to evaluate for like dissolves like. We need to evaluate which intermolecular forces would be present for each of these substances. Molecule number 1 is a straight hydrocarbon chain. Therefore, it only interacts through London dispersion forces. Molecule number 2 has hydrogen bonding available to it, as does molecule number 3. Molecule number 4, however, while it is polar and therefore it mixes better than molecule number 1, chlorine cannot interact through hydrogen bonding. So between 2 and 3, we can evaluate by seeing that molecule number 3 can interact with water through hydrogen bonding at 2 different locations, whereas in molecule number 2, only with the hydroxyl group on the right. So if we were to rank these overall, we would say that molecule number 1 has the lowest solubility, molecule number 3 has the highest, molecule number 2 has the second highest, and molecule number 4 has the third highest. And if you were to actually look up the solubilities of these substances in water, then that agrees with our assessment. That's it for this video. Thanks for watching. Have a great day.